Yeah, good evening once again. Today we want to talk about important topic, potential errors in measurement. Potential errors. Their potential errors doesn't mean that you make all of them when you are measuring, but those are possible errors that can be made while taking measurement. And when we talk about measurement, it's contextual. It ranges from data collection to estimation during study. For example, what I mean by estimation is like I want to know the prevalence of something. I want to know the mean. Whatever you are measuring, the way you are summarizing anything in the population, that is, which is their final measure in your study, is measurement also. For example, now, we want to know the prevalence of anemia and among other 5 in the community. If the prevalence of anemia is 30%, and you may end up saying it's 35 or 25 or 29, you may not get it accurately. It's still error. If you want to take measurement, maybe you want to take somebody's weight, and the person may weigh 74, and you measure 76, it's error, or 72 is error. So where it may apply to data, starting from data collection, you know that it is when the error that you make at the end of the day, maybe in estimating a particular population parameter, is due to accumulation of error during data collection. So from the level of taking measurement during data collection to the level of estimation for the whole study, there are error. Once you don't get you measure something, it's not the real value, which most of the times only God that knows the real value, is error. So let's look at this. So the difference between a measure, the meaning of error, what does error mean? The difference between a measured quantity and its true value. So it may be weight, maybe height, while you are collecting data. It may be hemoglobin concentration or PCV you want to estimate for a person. And you now say, oh, the PCV, it may be 35, and you say 36. The measurement in laboratory is 36. It's error. So if the average PCV or yes, the PCV, the average PCV in the study in the population, the sample you study, is maybe something like 38, and you say that the average PCV is 36%, is error. So the difference between a measured quantity and its true value. X is, that is the value, is equal to error, true value. What you measure is X, is equal to the true value plus error. So there are two components of the error. This E you see as error, there are two. We have random error and systematic error. So that error, that is, if you want to take measurement, you take a particular measurement. Whatever measurement you take is the true value plus error. So we say plus error. If maybe what you estimated is far higher than the true value, that shows that that E will be negative. If what you estimated is far less than the true value, that shows that the error is okay. The error is negative. If it's more than true, the error is positive. So, for example, now, if you want to take somebody's weight, and the person weighs 70 kg, and somebody says 71, and number says 69, both of them the same error, but in opposite direction. The same value, error of 1. But one is -1, one is +1. So now, let's now talk about this random error. You see, the error can be random or systematic. Random error occurs when a value of sample measurement diverges from that of the population due to a chance alone. If it's due to chance, it's not because of the way you carry out the study, not because you are negligent, not because you didn't take cognizance of something, but it's something that happened just by chance occurrence. That is random error. So random error causes inaccurate measurement of association. If when you are looking at association between two variables and doing your analysis. So sometimes what you estimate may not be the actual because of it may be due to random error. Systematic error is also called bias. When I say bias, it's the same thing as systematic error, another name for it. Occurs when results differ in a systematic manner from the true value. Systematic manner means that it's because of the way you carry out the study. If you have used a stringent measure, you have done it properly, the error wouldn't have come. So that is why it is systematic or bias. So it is, this bias is, you can call it overestimation or underestimation. Overestimation or underestimation of parameter of interest due to the way and manner the study was carried out. So I've already said error may be you overestimate or you underestimate, whichever way. Even the random error can lead to overestimation or underestimation. The same thing with systematic error, which is bias. But the bias is due to the manner in which the study was carried. It's not by chance. It is error caused by factors other than causes of random error. So if it is not random error, what causes random error that causes it? Whatever other thing that causes it is a systematic error. It's due to the way carry out the study. So this error now, you can summarize. We have said random error, systematic error. Under the random error, there are three categories. Individual biological variation. For example now, there's no, if you measure blood sugar, now in 2 minutes after you measure blood, it will know, if you can measure accurately, it should not be the same because, you know, things are going on. We said that much glucose is being consumed or is produced. Maybe if there's glycogenesis, if the liver is breaking down glucose, it may increase, or if the increase is not meeting up with your body, because as you are doing your activity, you are doing your thing, you are burning glucose also. So you may not get the same thing. Even blood pressure. You take blood pressure now, you take again, because a lot of things going on in the body. So there are those individual biological variation. For example, now if you want to do random blood sugar, fasting blood sugar rather, you say you should not eat until maybe you not eat after 10 o'clock and you come back. But if you come back in the morning, the person you take blood sugar from, blood sample from by 7 o'clock, what you get will be different from if you have taken it by 8 o'clock or by 9 o'clock, by 10 o'clock, 10 a.m. That's why they say that even when it's becoming like 10, you don't want to collect because the glucose in the fat, the stored glucose, the liver may be broken down to form new glucose. It may increase the blood sugar. So you can see, even within the time you have specified. So if you have taken it, you take for somebody at 9 o'clock, you won't have gotten the same thing if you were taking by 7 o'clock. As some people have come from 7, you started taking the blood. So you can see individual biological variation. So those are the, even though you are trying to be stringent, but still, you can never remove random error. Whether you even say, okay, all of them come by 7 o'clock, all of them, you puncture everybody at the same time. So those are individual biological variability. Even when they say somebody should not eat, the volume of food the people eat, the type of food the people eat, when last the person say you should not eat beyond 7. Some people have eaten the last meal by 6, 5 p.m. Some 7 p.m. Some 9 p.m. Some at 10 p.m. You may not go beyond. Those are, at the end of the day, whatever you get, there will be this biological variation. So it's one cause of random error. The other one is sampling error. Sampling error is error you get by the reason of taking sample. In as much that you didn't attend to the whole element in the population, whatever you are going to get can never be equal to when you take the whole population, that is, which is the parameter. So your estimate from the sample can never be equal to the parameter because of you have taken sample, you didn't attend. So you can reduce that one by increasing sample size. If you increase sample size, sampling error will reduce. The more the sampling size, the more that is, the closer the value will be to the parameter, the real parameter. Now, measurement error. This measurement error now is the way the limitation in measurement. Remember, within the limit of experimental error. That is, even when you are measuring, take measurement in laboratory. So you know that you are stringent because we are being human. So that's why we'll be rounding up to the nearest. For example, now you are measuring something in kg, kilogram. So you see, some people will say somebody more, both of them 75 kg. One may be 75 kg, 5 gram. Another person may be 75 kg, 15 gram, 20 gram, 200 gram, all those things. But just round of 75, all of them appear to have the same. So because of the limitation in measurement, so we call that one the limitation in measurement. No inaccurate measurement, the human limitation, no matter how stringent, that is the measurement error. Can you see now? You see, you can reduce them, but you cannot remove them. You can reduce random error, but you can never remove completely. The only one you can remove completely among them is sampling error. If you didn't take sample, you attempt to the whole population. You didn't take sample. In that situation, you have removed sampling error. But that is not the only source of random error. So it doesn't mean that you have removed random error. Because individual biological variation and measurement error is still there. You may say that, okay, individual biological variation is not applicable to something that has nothing to do with living thing. But what of measurement error? It has. So even if you are not dealing with measuring anything living thing, yes, individual biological variation is not there, and you take the whole population, no more sampling error, but there is still measurement error. I told you measurement doesn't have to be something you measure with and by eliciting response form of measurement. For example, now look at you want to measure grade of finger clubbing. Grade 1, grade 2. It's subjective. So how accurate or whatever maybe the way you measure depends on the experience and the expertise of the physician. So inexperienced person, the way you measure will be different. The one you call grade 3, it be grade 4 for somebody that's experienced. So those are type of measurement error. So let's come to systematic error. The systematic error is also called bias. So here we have selection, though they are about close to about 30, though they call them different type of bias, but actually they are causes of the bias. And these causes, people now use that, oh, those are the type of bias. That is the type of systematic error. They are up to about 30. But those 30 can be classified under 3 categories: selection bias, information bias, and confounding. So selection has to do with how do you recruit, how do you select. So it's different from sample size now. Yeah. How do you recruit people? That's selection bias. How do you recruit to the study before you even take the measurement? It's part of it because whatever you're going to estimate, I told you, measurement error is not only about data collection. Even the aggregate, the prevalence, the summary of the study, form of measurement. So the how you select participants will affect. If you, for example, actually give example. Imagine now somebody want to know the proportion of Igbos in Lagos. And then you now, if you go to Ladipo, you go to Festa, you go to Solo, you are likely to overestimate. But if somebody go to Idiaraba, go to places where maybe Apapa, there is most of the time the northerners that are there, you will likely underestimate the proportion of the Igbos. So whichever way, whether you go to where they are concentrated or go to where there are not many, there will be systematic error, that is selection bias. because the people you have selected now, because you know to know the proportion, you just to sample, and some will be Igbo, some will not be Igbo. For you to know, if you out of 100, how many are Igbos? In this situation, if you go to where they are concentrated, you are likely to overestimate. If you go to where they are less concentrated, you will underestimate. So that will lead to selection bias. So it's a bias, it's not random error, it's the way you carry out. So information bias, how you elicit information. You remember when, especially when we are doing all this randomized control trial, where you may say you have issue of blinding. We'll still talk about that. So let me confounding. So we talk. Those are the categories. So let me unpack everything with this slide. We still go over each of them. Random error. There are three major causes: individual biology variation, sampling error, measurement error. Random error may never be completely eliminated since we often study only a sample of the population. So since it's only a sample, we may not be able to even remove it. Not only that, for other reasons. Even in situations where we study the whole population, in case of finite population, when the population is very small, we can decide to study the whole population. Random error may still occur from individual biologic variation and measurement error. Sampling error is usually caused, it's not because of sampling. You know, sampling, when you say sampling error now, it's not the sampling method, which is selection. So the sampling method, what it affects is form of bias, selection bias. That's the sampling method. Sampling error just means because you sample, because you didn't study the whole population, that is it. So whatever error is bring, that is sampling error. It's not because of the way you sample. The way you sample, whether simple, random, or whatever, maybe you do purposive or you use systematic or you use probability method, this is part of selection bias. So sampling error is usually caused by the fact that a small sample is not representative of all the population variable. Individual variation always occur, and no measurement is perfectly accurate. How to reduce random error? The best way to reduce random error is to increase sample size. No, I've said it's a way. Because in fact, if you can study the whole population, you have removed the random error caused by sampling error. But doesn't mean that you have eliminated random error. But you can reduce it. You increase sample size. Measurement error can also be reduced by stringent, that is measurement error aspect of it. Stringent protocol. This is where you draw a protocol. This is how you take the procedure for measuring for in laboratory now. For anything you want to do, you have stringent procedure. If you follow it, you are less likely to, you can reduce the random error. Making individual measurement as precise as possible. So measurement error now. You see it? Now, researchers, let's talk about systematic error now. Researchers have identified over 30 different biases in systematic error. And there are different approaches used to classify them. However, the approach which is often used is group under three general categories: selection bias, information bias, confounding. So you see, this flow chart is just summarizing sources of error in the side. Random error, systematic error, which is bias, which are they are under three categories: selection bias, information bias, and confounding. Selection bias occur when there is a systematic difference between characteristics of the people selected for a study and characteristics of the people not selected. Just like what we have said, you want to know the proportion of some people, you go to where they are concentrated, that's selection bias. Or where they are not even plenty, that's selection bias. But if you different way to reduce selection bias, we talk about it later. An example is when participants select themselves for a popular study. If some people select themselves, okay, I want to take part. So the people that volunteer to take part in study on their own may be systematically different from the others because there must be something that is motivating them. For example, now, if they are giving there something you need to get in doing the study, people that have interest in that thing will tend to say, I want to do. The people that don't have interest, they are not interested in that benefit, will say they are not interested, they will not do. So that is why when you talk about selection bias, so when somebody presents himself, so is what do I call it? If we can call selection bias, those who choose to participate may be different in some important way from those who choose not to participate. So look at just to demonstrate this one. Look at audience bias subset. So if you look at it, maybe the person just selected some people. You will see that all those people they selected, they have some things in common. So maybe they have afro, their head is somehow the same pattern. So that's selection bias. The people selected are quite different from the other in some ways. Information bias, you also call it observational because observational, classification, or measurement bias. Measurement bias is different from measurement error. Measurement error is a form of random error. The measurement bias is a sum of systematic error. So information, observation, classification, measurement bias is the same. It shows that it is when you are eliciting response. Can you see? Selection bias has to do with when you are selecting, when you are sampling. You are selecting people to participate. That's where selection bias also occurs. The information bias is when you are eliciting response, you are collecting the data. That is where information bias. So you know that in data, in statistics and research, when we talk about observation or measurement, it means the same thing. It means data collection. For example, now, if you want to measure somebody's weight, you say stand on the weight scale. You may say it's measurement you have taken. But if you want to observe finger clubbing, you observe yourself. You want to observe jaundice, you observe it yourself. You look at it, you may say it's observation. If somebody is a male, you don't need to ask, you have seen. But you may want to ask some question. Oh, what did you eat? What's your religion? What's your ethnicity? All those things. Or as far as statistics is concerned, they are either, you call them observation or measurement. You are eliciting, or classification, you are eliciting response. You are getting information. You are eliciting response. You are collecting that data collection. So this information bias occur during data collection. This occur when individual measurement or classification outcome or exposure are inaccurate. They do not measure correctly what they are supposed to measure. They are inaccurate. So before we talk about prevention of bias, let me expatiate more on this classification. For example, now, when we talk about recall bias is a form of, I've already said that it's under this information bias. You can just list different type of bias. Some of them can say they are a form of selection bias or they are a form of information bias or confounding. Recall bias now, when somebody need to remember something, it usually happen in a descriptive cross-sectional study or case control study when somebody need to remember something. So recall bias is peculiar with case control, where in case control, you start with, okay, these are people that have this case. For example, maybe you talk about varicose vein among women. You want to see does intake of ACP, oral contraceptive pill, result in varicosity. So in this situation now, you recruit people that have varicose vein all over different centers. You now recruit some people also, they don't have varicose vein. But they are in some context about age-wise, many things, they may be similar with the other people, but they don't have varicose vein. So that's what we call case and control. Now, you want to ask if you want to know if OCP contribute to the varicosity. So you have those people that have varicose vein, you have them history of OCP intake. For how long? So you ask. The people that don't have varicose vein, you see have the same thing. But the core bias occur when people that have problem are more likely to have remember that they were exposed to the incriminated factor than the people that don't have. Because the one that have varicose vein, you're asking, do you take OCP? Even if the person did not even take it very well, he didn't even take it, you will think, oh, wait, so can it be the cause of my problem? And I say, yes. Did I take it? I think I took it. Yes, I took it when I was in London. I took it for 3 years. So the person, because he has the problem, is likely to remember that he took. Somebody that doesn't have problem, you just say you recruit the person into study. Just simply you will not take your time. You ask him. He will say no. He will not even remember because he doesn't have problem linked to that you are asking. So did you take the? No. Even if you say take it for how long? I didn't take it much. I cannot even say I took it. No more than 1 week. You know, that is what we call recovery. The people that have problem are more likely to remember that they were exposed to the factor, incremental factor. Why the people that don't have the problem, head problem, will not likely remember. And it will give impression that more impression. It will overestimate the association between the disease and the factor. It will give more impression that, oh, it's that thing that's causing it. Because we see more of the people that have the problem, they say, they did it. They report being exposed. That's recovery. So we also have issue of information bias, which can be prevented. Okay, anyway, I think when we talk about prevention, we talk about that blinding. Prevention of bias. Prevention of bias, selection bias, same selection criteria, high response rate, high rate of follow-up. Then prevention of information bias, clear definition, good measurement method, blinding, standardized procedure, quality control. The meaning of blinding. So blinding is when you prevent whether maybe only the participant or the investigator or the analyst from knowing which group do any participant belong to, whether it's in the control group or in experimental group. Because in experimental, so this blinding is peculiar to experimental design. For example, now, if there's a drug you make to treat hypertension, and one of the things you want to ask is that you ask question apart from measuring the blood. You don't ask question about blood pressure. Ask, is your blood pressure has it come down? No, you take measurement. It's subjective. But you need to ask some subjective question. Maybe the drug also, they have to be able to, if they don't have the symptom is not being disturbed, they'll be able to sleep very well. You don't have headache. No, you may say, did you sleep? So the person, if the person know that it's in the active drug group, so when you say, did you sleep? If he didn't sleep, because he's aware that we are the one that are taking the drug, there are some people the are giving it is not the drug. So I think I slept. Even if you didn't sleep, so he will give you information bias will be there. In the sense that he will tell you, because he's aware that that drug, if you take it, you should be able to sleep very well. So he will tell you, no, he didn't sleep. Whereas the person that is taking is aware that is taking is in control group. He knows that it's not the active drug. Even if the person slept very well, we say that, okay, he is aware that he's not taking a drug. Is that actually sleep? I see, because he's aware of where it belongs. So to prevent that information bias, you blind them. When you blind him, blind is the say he doesn't know what he's thinking. They just know that he's doing study. Doesn't know the control group, they still give them something, it's placebo. They give them something as if they are taking drug, but it doesn't have active ingredient. So they give all of them drug. To them, they are taking drug. So nobody is aware whether it belongs to experimental or no. They are just taking drug. So though they may tell them that some of them they are not, it's not the best, they don't know. They don't know where they belong. So the person does not know where it belongs to. So it will prevent him from from giving wrong information. You just say it the way it is. So you prevent that information by. That type of blinding is called single blinding, because only one person you blind. Only one party, which is the participant. Then, if the participant is blinded and the investigator, the person eliciting response, administering the questionnaire, asking the question is not blinded, there will be a problem. Imagine now, someone does not know where it belongs to. Maybe it's in experimental or placebo group. So you say, did you sleep? Tell you what he felt. And you know that it's in the active drug group. When the person say that he didn't sleep, that's, are you sure? So as you approve it, are you sure that he didn't sleep? I was okay, slept. Because you are aware that it's in the active drug group. So the investigator may begin to probe unnecessary probe. By the time you probe, they succumb. They will now say, okay, this is what you expect them to say. They will not say what you expect. The same thing, if you know that as the investigator, you know that somebody is not in the active drug group, and the person say that he slept, you know, are you sure? Well, I didn't really sleep like that. Because you are inflamed, because the person know that he didn't take the dog, he's not supposed to say he has slept. Too. Can you see now? So if you prevent that person from that, if you prevent both the participant and the investigator, that is double blinding. The third one you can do is when you prevent both the participant, investigator, and the data analyst. Because if you are doing it and a statistician know which one, say group A is this is experimental, this is control, and he's running it, and the analysis is not going, this one is not biologically plausible. Begin to can change, begin to adjust. No. Begin to trying to do the analysis to find something in favor of the experimental, because he knows which group is experimental, which one is control. So you may, if you want to, the people that design the study can blind everybody, including the data analyst. They will seal it until it's after they have finished the study analysis before they bring it out. So you can just say purple and green. So they will not say group 1 and 2. They green, purple. So we don't know which one is number 1, which one, or we don't know which one is experimental. In the background, they are already sealing, they know better. All the people that are involved in the study, the participant, investigator, data analyst, they don't know. They don't know which one is active, which one. They just know there are 2 groups. They do the analysis. That's triple blinding. That's the way of preventing information bias. Standardized procedure, quality control, all of them. Now, the last aspect of bias is confounding. What is very, very important, this one. And this is the reason I actually give this lecture, because that's the reason for doing all this multivariable analysis. You say you are removing confounder. When you do logistic regression, ANCOVA, multivariate maneuver, multivariate analysis of variance, multivariate analysis of covariance, all those things. You are doing all sorts of statistical method just to remove confounder because of this. So confounder occur, confounding occur when a variable is associated with the exposure and it affects outcome. Can you see? One variable is associated with, when you say outcome and exposure, there's you are studying relationship between two variables. One is the exposure, one is the outcome. For example, exposure to cigarettes, lung cancer, or exposure to hair, cigarettes, or cigarette or tobacco, and heart disease. It's an example. So you know that, okay, the outcome measure is heart disease. The exposure is tobacco exposure. Now, there will be another variable that is associated with tobacco, but on its own also can lead to heart disease. For example, coffee. Coffee may contribute to heart disease. Coffee is associated with tobacco in the sense that both of them are substance use. Let me see. See, that's one. Okay. Coffee. Okay, this one is actually association between coffee and tobacco is a confounder. It can be association between tobacco and coffee will be a confounder. It's that way. Now, the reason, if you look at it, look at the arrow. The exposure of interest will lead to outcome. Yes. It can cause heart disease. The other one also can cause heart disease. But both of them are related in the sense that both of them are substance use. So how will you know? If they say among the people that take coffee and people that don't take coffee, who will more likely to use tobacco? You know that people that take coffee will be more likely to use tobacco than the people that don't take coffee. The same thing, among the people that use tobacco and people that don't use tobacco, who will likely take coffee? The people that use tobacco will more likely take coffee than the people that don't use tobacco. So that is why. So is related, the confounder lead to the exposure also, but it's related to the exposure. So it leads to the outcome rather. The confounder leads to the outcome, but it's also related to the exposure, but it's not in the causal pathway to the exposure to the outcome. What it means that it's not as if maybe the confounder will lead to the. It's not as if the exposure will lead to the confounder before the confounder lead to the exposure into the outcome. It's not as if maybe if you are taking coffee, you'll be taking tobacco by force. Because when you take coffee, that lead to take tobacco. Tobacco will not lead to heart disease. No, it's not in the causal pathway. But the issue is that both of them, that is, they lead to outcome, but they are associated as a confounder. Now, this is another example. You see, alcohol leading to lung cancer. You want to study. So smoking, that one will lead to lung cancer. And alcohol and smoking, they are related. Because if somebody that drink is more likely to smoke than the person that doesn't drink. And somebody that smoke is more likely to drink than the person that doesn't smoke. So you see, drinking and alcohol and smoking, they are related somehow. So the method employed to remove confounder. This method, there are five different methods. 2, 3 are employed during the science stage of the study. 2 are employed during data analysis. The 3 that are employed during studies design is randomization, restriction, and matching. What's the meaning of randomization? Randomization is the hallmark of experimental design. That's what make it experimental, I say, the hallmark. And the meaning of randomization is selection into control and experimental group just by chance. Like if somebody finds himself in a control group, it just happen as you are selecting randomly. You know, actually somebody or is determined. So randomization, you may say you are just balloting and okay, this one will go to this one. Maybe you can even when the participant they are, I give them paper, just put paper, you pay some, you write group P, experimental control, you may write. So people pick. At random they pick. Whatever they pick is what they belong to. So that is you have done randomization. In as much that the people that find themselves in the experimental group is just by chance. The people that find themselves in just by chance. That is randomization. Restriction is when you know that something is a confounder. So you now, okay, anybody, you know, you are studying exposure to alcohol. Anybody that has that confounder, you eliminate it. For example, now, in the issue of coffee to heart disease, anybody that takes tobacco is out. It will not be part of the study. You restrict them to those people that don't have that variable, that restriction. But sometimes when you do restriction, you may have issues. You may not easily find enough sample size on time. Then marking is, you know that confounding variable, whenever you recruit one person, maybe you see one person that the confounding variable, and the person you can put, if there are 5, you do them equal. That is, if you have one person here, experimental group, in one group that have the exposure, that have the confounder, you also have another person in the other one that have the confounder. You make sure that those people that have that confounding variable, they are equally shared among the two groups. That is matching. So, but the problem we have with matching, sometimes people match for too many things because the major confounders in any study are socio-demographic variables. Age, sex, ethnicity, religion, all those things, all those socio-demographic, they are main confounders. They are the confounders, major confounders. And that is why it's non-accident that many times when you are doing study, you always have this socio-demographic. So you have to ask questions about them because those are the factors you go to eliminate when you do your regression to knock out which one is a confounder. You don't want a confounder. You don't want an association that is affected by a confounder rather. So you match. So now those are the 3 methods you use during the design stage. The other 2 methods you use is during data analysis. So anything you cannot remove during design stage, you want to remove it during data analysis. For experimental design, by the time you do all this randomization, restriction, matching, you have removed almost all the confounder. You may not need to even do rigorous analysis. No, but people that are doing observational research are not experimental because most research are observation because you know all the situations you can perform experiment for ethical reason, especially on human. Even say animal has right now. Even animals say, remember I said that you should not, they are being also. So they are ethical principle guiding the task of even animals. So that's why experimental research is not common like observation. So if the person has not performed of course there may be a lot of confounder to use this method. Stratification or stratified analysis and statistical modeling. Stratified analysis just means that, you know, you have a confounder now, you now, okay, you analyze separately for the people that have the confounding variable. You analyze separately for the people that don't have it. So, can you see now? If actually there is an association between the exposure and outcome, the association will be the same, even in the two. When you run the association, to be exactly the same thing for the people that have the confounder and the people that don't have the confounding variable. Then statistical modeling. So that's why you use regression, what they call multivariable analysis. Though some people call it multivariate analysis. It's not true. If you read standard textbook on statistics, those regression, linear regression, statistical regression, they are multivariable analysis because it's only one outcome, but you may have many exposure, many variables that are exposure, but one outcome. But the one they call multivariate analysis, many outcome, many exposure. Maybe the outcome you are measuring is not only just one, more than one, and the exposure more than one. That is multivariate analysis. Like example is multidimensional scaling, factor analysis. Those are the multivariate analysis of variance. Those are multivariate analysis. But regression is multivariable analysis. Thank you. Any question? Any question?
Thank you very much, sir.
Yeah.
Okay, this last slide, I understand it, but what I'm just asking, if you use restriction to employ during the study design, and you're trying to remove those that have the confounding factors, or if you are the risk, for example, the risk of heart disease, and you're using smoking and then removing those that have that take alcohol as well, which is a confounding factor. Wouldn't that reduce your, or you just pick one of the three methods, or you don't have to use the three methods employed. You just pick the one that works best for the situation, I guess. Like you don't
Sometimes you
have to
can
use
use more than one.
eh?
You can use. The more you use, then the more you are removing the bias. Confound is a form of bias. So as much as you can do possible to enrich the study. Now, maybe the question you wanted to ask, that restriction, sometimes when you restrict some people, just like you say, exclusion criteria, when you have too many exclusion criteria, when you do your study experimental design, so what you actually, if for a drug that you want to know the effect of drug, what you are studying is more like efficacy of the drug. The effectiveness of the drug is not what is efficacy. Because efficacy in ideal situation, when you remove everything that may serve as controller, for example now, anybody with comorbidity, epilepsy, out of it, sickle cell, out of it, asthma, out of it, anything out of it. But in real life, that condition you are trying to study, it doesn't exist. Somebody can have heart disease and have epilepsy, can have heart disease and is a sickler, can have heart disease and so asthmatic and all those things. So you discover that. So the thing, whatever you study, since you have removed all those people, it's an ideal situation, not a normal situation. So in real life now, so that is why when you draw real life, you need to study. You need some observational study to study what happened in real life. Because most of the time, that's why they say the external validity of experimental design is lower than that of observational design. to external validity of observational studies higher than that of experimental design. The internal validity for experimental research is higher than that of observational. So I don't know if that one answer your question. Any
Are you
other
saying
one?
are you saying that these methods are not practical?
They are practicable, but let me tell you something. They are practical to different degree. You know, they say there's something, maybe I didn't make mention of it. They say that, we said that we cannot completely remove random
Bias.
error. But it is said that you can completely remove systematic error, which is bias. But to me, as person, I don't believe.
I don't believe it.
That you can completely remove it because from what look at what you raised now. So sometimes some people say I did randomization. They see some people may not even do everything. Some people may even do it the way they did it. So the way you are being stringent in your protocol and the way the experience and your expertise vary with people. But the fact that they say somebody is expert, we are all expert, but some are more expert than the other. So it's just like the Holy Book that says, "Be thou perfect as your Father in heaven." But that is the target now. They say you can be perfect. If you cannot be perfect, God cannot put it there. But have you seen anybody that is perfect? It's the same thing for that systematic error. To me, nobody can. You cannot completely remove, but you can reduce it drastically, but not completely. So, Dr. Olanino, you raise hand. Go on.
Thank you, sir. Good evening, sir.
You
My own question, sir. When we're talking about the random error, why selecting that increasing the size can help us reducing the selection error of the random error. So
random error is not selection by random error. Yes. Increase
so
sample size.
I'm not asking that how, because normally they will say, okay, 10% addition or 10% on response something. I mean, to add 10% to whatever sample you calculate. So going over that 10%, how will one explain that? Will it not be like, oh, you are wasting resources once you have your sample size? How wide can we?
Well, the issue there is the higher the sample size, the less the random error. So the issue here, this issue of 10%, actually most of the time address the issue of power of the study. So the power is ability to find what you are looking for if it's actually there. So if the sample size also is very small, for example, and the 10% is because of the non-response or attrition. You know that some people may not respond or they fall away. So if you have calculated the minimum sample size, you will be able to find the difference you are looking for. And something now happened concerning some variables here. They didn't respond. If some people did not respond, the people that responded are short of the calculated sample size. So if you don't find the difference, maybe because the power has been compromised. In order to find that, that's why it's okay. We look at the non-response rate in the environment. You increase the sample size based on the non-response rate. So that even if that number of people, that proportion of people leave or they didn't respond or there is attrition, whatever is left is we still have the power, require power to find the difference. So, but by increasing the sum also, it will anyway do whatever, whether because you are trying to give room for non-response, whatever. By increasing the sample size, you are reducing the random error. So, of course, they say it cannot be completely removed completely, but you can improve on it. So, issue of wasting resources, yes, sometimes resources are limited. So the target here now is the power of the study. It's not the much about the error completely, because you know that you cannot remove random error completely, but at least you can reduce it. But the power of the study, if the power is nothing, that is is low, you may not be able to find the difference you are looking at. So that is why
Okay, sir.
once you are able to have the minimum sample size that will not compromise the power, every other thing, some people believe that you are wasting resources because we have the other thing you need to spend money on. You need to do another research also. You cannot spend all the money on one research. You need money to do other research that will be beneficial in another way. I don't know if that answers your question. Any other one?
Yes, thanks, sir. Is there a way we can reduce recall bias? Then I didn't get that explanation for methods used for doing analysis to reduce confounder to control stratification. Can you go over that?
Stratification means stratify analysis. Stratify analysis that, for example, you have, in this case now, tobacco is the confounder. So you recruit people there, both with people that take tobacco, people that don't take tobacco. But when you are doing your analysis, you separate the people that take, you divide them into two. People that take tobacco, people that don't take tobacco. And run the analysis association between coffee and heart disease for each of them. That's what we call stratified analysis. And that's what we use Martin I-square to do. So by doing that, you remove the effect of that tobacco,
Okay.
the confounding effect.
What about recall bias, sir?
Recall bias.
Is there a way to reduce it?
Well, that one, I don't think there's any way to reduce it because that one, especially for case control, is inherent. That is a major problem with the study design. Somebody that you recruited somebody that have problem, you are asking question about what you think is causing it. And some people don't have the problem, asking the same question. So it's a natural thing. The people that have problem are more likely to remember that they were exposed than people that don't have the problem. So you cannot, in sense of reducing, I don't think it's one of the major problems of, in fact, it's number one problem of case control study. I know that one.
Okay, thank you, sir.
Welcome. So even though, can you see now, people will say that they can reduce, they can remove it, unless you substitute the study, you didn't do case control. So what will you ask your question? So is your memory that somebody naturally will remember something because it's suffering? The other one will not remember because it doesn't have problem. And you see, when they say they can remove bias completely, it's not possible. You can reduce it. Or there are many causes, so say about over 30. So step by step, at the level of selection bias, if you remove different type at the level of information, then confounding, you reduce. You are more strict with you are stringent with your protocol. So you'll be able to reduce the systematic of this bias. Any other one? Okay, I think if there's no question, stop here. Thank you for listening.